Welcome to Pre-Calculus Honors.
Okay, so here we have our multiple angle and what we call product to sum. Let's talk about double angle identities. Okay, double angle identities are, first of all, a double angle is when your angle has changed. So let's just talk about what that means for a minute. If I have 2 sine x, okay, that's just sine x plus sine x, right? So for example, if I have 2 sine of 50, that's just sine of 50 plus another sine of 50, okay? Now, as opposed to if I have sine of 2x, okay? Now, if sine of x equals sine of 50, then what's sine of 2x? Sine of 2x is sine of 100, okay? So do you see what happens? In the one case, you have sine of 50 twice. Okay, sine of 50 plus sine of 50. In the other case, you had sine of 50, but when you double the angle, your angle changed to 100. So you went from first quadrant to second quadrant, if nothing else. Okay? All right, so that's the difference between sine of 2 theta and 2 sine of theta. Now, we have identities for sine of 2 theta and cosine of 2 theta and so on. The one for sine 2 theta is 2 sine theta cosine theta. So they relate back to the single angles. And here's the one for the tangent. It just includes tangent of theta. Now, for cosine of 2 theta, you have 3 choices, and they're equally as valid. You just use whichever one happens to be most convenient. All right, so let's do the first one here. You have sine of theta is 3 over 4. And you want to find sine of 2 theta, cosine of 2 theta, tangent of 2 theta. Now if you look above, all of those identities involve sine of theta, cosine of theta, and tangent of theta. So before you even start with the double angles, you have to use the identities from 5.1 and find cosine of theta and tangent of theta. So just find the other two. So use identities from 5.1 to find cosine of theta and tangent of theta. So first off, we have sine squared theta plus cosine squared theta equals 1. 3 over 4 squared is 9 over 16, plus cosine squared theta is equal to 1. Cosine squared theta is 7 over 16. So cosine of theta is plus or minus root 7 over 4. I'm going to take the positive. And then it'll fix itself. In your homework, you have a more specific, In your homework, you have a more specific quadrant, okay, and then you'll know exactly which one to pick. So that's cosine of theta, and then tangent of theta is sine theta over cosine theta, meaning it's 3 over 4 times 4 over root 7, so that's 3 root 7 over 7. Okay? Now let's go to our multiple angles. So first I'm going to do sine of 2 theta. This is equal to 2 sine theta cosine theta. So this is equal to 2. Sine of theta is 3 over 4. Cosine of theta is root 7 over 4. That means sine of theta is, this cancels with this, you have a 2 here. So 3 root 7 over 8. Okay? All right. Next one, I want cosine of 2 theta. Now, for cosine of 2 theta, I have 3 choices, and I can pick any one of them. Let's pick the second one. It might be easier. So the second one says 2 cosine square theta minus 1 is what cosine 2 theta equals. So 2 cosine square theta is 7 over 16 minus 1. This is 7 over 8 minus 1, which is how much? Negative 1 over 8. Now, tangent of 2 theta, okay? You can either use this formula, this identity, all right? But if you've already got sine 2 theta, cosine 2 theta, you can just divide and get tangent 2 theta, okay? You use this, use when given tangent of theta only, all right? Now, that's not a law. You can definitely do that. It's just so much unnecessary arithmetic, okay? So tangent of 2 theta is sine of 2 theta. Just make sure that your angles are consistent over cosine of 2 theta. So that's 3 root 7 over 8 times negative 8 over 1. This is negative 3 root 7. Okay? Just make sure that these angles are all consistent. 2 thetas. Okay? All right, we use these to solve equations. All right, just like we don't like to mix different trig functions when you are solving an equation, similarly, we want our angles to be consistent. So I don't want to have 2 theta and theta. I can't have 2 theta and theta in one equation. Okay? So we have to convert all angles to the same one. What I want to do here is I want to substitute for cosine of 2 theta its identity. Well, what is cosine of 2 theta equal to? Right. I'm going to choose the middle one because I am working with cosines. So that's going to be 2 cosine square theta minus 1. And then I have minus cosine theta equals 2. So now what do I have? I bring everything to the same side, so on and so forth. So I have 2 cosine square theta minus cosine theta minus 3 is equal to 0. I'm going to factor 2 cosine theta and cosine theta, and I have a minus 3, and I have a plus 1 equals 0. So cosine theta is equal to 3 over 2, and cosine theta is equal to minus 1. So now, for which angles is cosine equal to 3 over 2? None. Why? Right, and 3 over 2 is greater than 1, which is out of the domain, so there is no solution there. Here, where is cosine equal to minus 1? At pi. So theta is equal to pi. And that's the only answer there. Okay? Now. No. That's, okay. So now, what we're going to do, sometimes it is necessary to use one of these identities, but sometimes like you have to solve for cosine square theta. You see what I mean? So sometimes they give you cosine 2 theta, and you have to reduce, and you have to find cosine square theta, or, you know. So let's solve this for cosine square theta. Actually, I want to solve this for sine square theta. Can we do that? There is a mistake on your packets here. This should be 2 sine square theta, and this is sine square theta. The 2 is misplaced. So go ahead and fix that. All right, so I'm just going to solve that identity. I just copied that over from the top, okay? That's where it comes from. And just for fun, I'm going to solve it for sine square theta. Can we do that? So if I want to solve this for sine square theta, what would I do? I would subtract the 1. So negative 2 sine squared theta, or rather 2 sine squared theta is 1 minus cosine 2 theta. Right? So what's sine square theta? 1 minus cosine 2 theta over 2. Okay? Well, what does that do? That takes your function with an exponent and changes it into an expression that has no exponent. So sometimes it's necessary for us to eliminate powers or eliminate exponents, and that's when we can use this one. Okay? So we use this to eliminate or reduce powers. And that's why it's cleverly called a power reducing identity. So it doesn't come out of the blue. It's just the ones from the previous page rearranged. Okay? How do we use this one? Well, here I have cosecant to the power of 4 theta. And I want to write it in terms of cosines and sines, or in terms of just cosines of multiple angles with no power greater than 1. Okay? So you see how you have an exponent of 4 here? I want my answer now to have no exponents other than 1. But I can have multiple angles. I can have 2 theta, 4 theta, 6 theta. Okay? So here's what we're going to do. What's cosecant like? Sine, cosine, or tangent? All right, so this is 1 over sine to the 4 theta. Okay? Well, that's fine, but I want to write this as 1 over, because I don't have a formula for sine to the 4, but I do have a formula for sine squared. So is it possible for me to say, hey, you know what, this is just sine squared theta squared? I can say that, right? Okay, now, what's sine squared theta? Sine squared theta is 1 minus cosine 2 theta over 2. This is sine squared theta. Here I have the reciprocal. So I'm going to take that and flip it to the reciprocal and put it here. Okay? So it's going to be 2 over 1 minus cosine 2 theta squared. Everybody with me? Now, I am going to distribute the square. Okay? So it'll be, in the numerator, a 4. In the denominator, I FOIL, so I get 1 minus 2 cosine 2 theta plus cosine squared, what? 2 theta. Okay? Now, okay, so I'm good here. This is an issue. I still have a power greater than 1. So I have to apply another identity. Okay? Now, here I have a cosine squared. Where is my cosine squared identity here? Right there. Okay? So if I call this number 1, I'll call this the number 2 identity. What I'm going to do is I'm going to substitute that into here. Now let's take a closer look here. This says cosine squared theta is what? 1 plus cosine of what? 2 theta. Now look, this is theta, this is theta. If instead of theta here I had x, what would that be? 2x. Okay? If instead of theta here I had table, what would that be? 2 table. If instead of theta I have 2 theta, what would that be? 4 theta. All right? Here I have 2 theta. Okay? So, here's what we're going to do. This is 4 over 1 minus cosine, 2 cosine, 2 theta plus, I'm going to substitute for this, that one. So it'll be 1 plus cosine 4 theta over 2. And that just looks like such a simple little equation, doesn't it? Such a simple little fraction. Now I have to simplify that fraction. Now, after this, it's pretty much algebra. Because this says whatever the angle is, you have to double it. Here the angle was 2 theta, it gets doubled. Okay, so now let's do some algebra. All right, how are we going to do this? This is a numerator of 4 over. Now here I want to make a common denominator. That means the denominator of that part will be 2. Okay? And here I just multiply this by 2 over 2 and this by 2 over 2. So it'll be 2 minus 4 cosine 2 theta plus 1 plus cosine 4 theta. Okay? Now, is this a minus or a plus? It's a minus, right? Here. Okay. So now, what do we have here? We have a... Okay, so can I multiply these two and get 8 over 2 plus 1 is 3 minus 4 cosine 2 theta plus cosine 4 theta, and you know, I think I'm done. All right, so now I have exactly what I wanted. Cosines of multiple angles, 2 theta, 4 theta, with no power greater than 1. That's exactly it. Okay? Honestly, like if that doesn't... In this one, we're going to solve an equation using the power reducing identity. So the issue here is that we have a sine mixed with a cosine. But I know now what sine squared theta is. And the fact that I have cosine 2 theta tells me I can't use, you know, sine squared plus cosine squared equals 1, right? I have to use one that involves, that connects the square with the multiple angle, okay? So this is equal to 1 minus cosine 2 theta over 2 plus, now I have cosine 2 theta minus cosine theta equals 0. And I really don't like that 2 in the denominator, so why don't I just multiply everything by 2 and it'll automatically go away, right? So I will have 1 minus cosine 2 theta plus 2 cosine 2 theta minus 2 cosine theta equals 0. What do I have now? Now I have, when I combine these, I have a 1 plus cosine 2 theta minus 2 cosine theta equals 0. Okay? Now, I still don't like this because now I have a 2 theta and a theta, which doesn't work. I can make another substitution. What's cosine of 2 theta equal to? Well, with the one we like is, right, that one. And the rest of the equation is 1 plus this minus 2 cosine theta is equal to 0. These go away. 2 cosine square theta minus 2 cosine theta is equal to 0. Divide through by 2. Actually, let's just combine steps. We can take out a 2 cosine theta, and we get cosine theta minus 1. So here I have that cosine theta equals 0. Cosine theta is equal to 1. And I know that cosine theta is 0 where?
0. Oh, it's 0
at pi over 2 and 3 pi over 2. And to this, I'm going to add 2n pi. And where is it equal to 1?
0.
At 0 and 2 pi, right? So it'll be 0 plus 2n pi, which is just 2n pi. All right. I know. Yeah, so the next ones are your half-angle identities, okay? All right, so when do we use half-angle identities? So suppose you have to find sine of 15. 15 is not a special angle, but it's half of a special angle, all right? This is really sine of 30 over 2. And when you do that, you say, oh, okay, so 15, wait for it, is half special, right? Because it's half of a special angle. So similarly, half of 45, 22.5, half of 135, half of all the, like 210, all right? So all of the special angles can now also be related to the half angles using this formula, okay? In these identities, the theta is the full angle. So for example, if we're looking at sine of 15, then theta is 30 degrees. You see what I mean? Say yes.
Yes.
Good. All right. So let's find sine of 22.5. Well, this is really sine of 45 over 2, meaning this 45 is your theta. All right? Now, what's the identity for sine of theta over 2? Well, it's this one. So we say sine of 22.5 is equal to plus or minus the square root of 1 minus cosine of 45 over 2.
So we're
Now,
use degrees in these?
well, if your question is in degrees, then yes. If it's in radian, then you use radian. Now, do we use plus or do we use minus? Well, you look at your theta, okay? Whatever quadrant theta is in determines the sign, the plus or minus, okay? So theta is in quadrant 1, so we're going to use the positive one, all right? So now this is going to be the square root of 1 minus, what's cosine of 45? Root 2 over 2 over 2. So this is over 2. Now what's the numerator? It's going to be 2 minus root 2 over 2, which is going to be the square root of 2 minus root 2 over 4, which is going to be the square root of 2 minus root 2 over a 2. And all math teachers love the fact that you get a root and a root.
Does that happen often?
Well, in half angles. Okay, so that's the answer there. So the things to remember are theta is your double, the double of the angle, the full angle, and that determines the plus or the minus. Okay, so how do we apply this in an equation? Okay, we have sine squared x over 2, cosine squared x over 2. Well, guess what? We can write this with the power outside. So like this. This is really, this is really sine of x over 2 squared. Is that right? And this equals cosine of x over 2 squared. Well, what's sine of x over 2? That's just the formula, right? It's plus or minus the square root of 1 minus cosine theta over 2 squared equals 1 plus or minus the square root of 1 plus cosine theta over 2 squared. Now, the square does two things. It gets rid of the square root and it gets rid of the plus or minus, because when you're squaring, everything is automatically positive, so the plus or minus is irrelevant. So now you have 1 minus cosine theta over 2 equals to 1 plus cosine theta over 2, and that's just a uninteresting little equation, right? Because the 2's go away, and you have 1 minus cosine theta equal to 1 plus cosine theta. And once the 1's go away, you just have 2 cosine theta equals 0. So theta is what? Pi over 2, 3 pi over 2. Okay? I'm telling you.
It's like an accordion. Exactly. Yeah.
The unit circle is like, it's really like at the base of all life. I'm telling you.
People base religions off the circle of life. We need to create
Yes.
religion around it.
Yes.
Whoa.
So one thing you always come across in calculus is the product of two trig functions with different angles. All right, so the product of two trig functions with different angles, that's the key. So for example, you know, here you have cosine times sine, but the problem is that it's not cosine 2x, sine 2x. They're different angles, and you can't do anything with that. To simplify those functions, what we have are product to sum identities. So literally what this does is take a product and expand it to a sum. Okay? There are 4 of these. So you have sine of something else, cosine something, cosine of something else, and then you have you know, all the different permutations, sine, cosine, cosine, sine. All right?
So if you have tangent,
we can work around that. All right, so here, this is just a plugging in. There is nothing too exciting about this problem. We're just going to use one of the identities to expand this one. So if you have cosine of alpha, cosine of beta, which one of these are we going to use? We're going to use number 2. So it'll be half, in brackets, cosine of alpha minus beta, so 6x minus 3x, cosine of alpha plus beta, 6x plus 3x. So this will be half cosine 3x cosine 9x. Oh, where's the plus? Here. Oh, hey. In here, there is a plus. So it's half cosine 3x plus cosine 9x. And you can either leave it like that, or you can distribute the half. And it'll be half cosine 9x. Doesn't matter. Doesn't matter at all. Okay? So here you have sums of two trig functions can be combined. Now you can go in the opposite direction. And if you have a sum, you can condense it to a product. And again, you have 4 of them here. For the first one, which one are we going to use? The third one. So it'll be 2 cosine of 255 plus 195 over 2 cosine of 255 minus 195 over 2. So this is going to be 2 cosine of, and we actually get cute little angles for this one, 225 and 30. This gives you 225, and then cosine of 30. Now, I know exactly what cosine of 225 is, because the reference angle there is what? 45. And it's always root 2 over 2, except in the quadrant where 225 falls, cosine is negative, so it's negative root 2 over 2. And now everybody knows that the cosine of 30 is a half, right? What is it? Are you sure?
Yeah.
We're at 3 over 2.
You had me questioning myself.
That's right. Okay, so now we have negative root 6 over 2. All right. All in a day's work. Here we're going backwards. Which one are we going to use for this one? Sine 8x minus number 2. So we get 2 sine 8x plus 2x over 2. Oh, no. Yes, cosine. And then sine 8x minus 2x over 2. So this is 2 cosine 5x sine 3x. Oh, no. No, of course not, because this is an equation. So we set this equal to 0. Ooh, this is getting interesting.
This got good real fast.
This got really good all of a sudden. So now, cosine of 5x is equal to 0. Oh my God, look at this one. Cosine of 5x is equal to 0. Sine of 3x is equal to 0. Where is cosine 0? Come on now. Pi over 2 and 3 pi over 2. That means, stay with me now, this entire angle must be pi over 2 or 3 pi over 2 for the cosine to be 0. So that entire angle, 5x, must equal pi over 2, or 5x must equal 3 pi over 2, okay, for it to be 0. Either or. Okay? So now what's x equal to then? Pi over 10. And x here is equal to 3 pi over 10. Now, this is over the interval negative to positive infinity. Okay? But, if it was sine of x, it would repeat every 2 pi. Now we have sine of 5x. That's a much shorter period. So 5x repeats every 2 pi. So x repeats every 2 pi over 5. So now this is going to be plus 2 pi over 5 plus 2 pi over 5 n. Right? N. Told you it was getting exciting.
My heart rate's skyrocketing.
This one, 3x must equal 0 or 3x must equal pi for the sign to be 0. That means x must equal 0 or x must equal pi over 3. Well, now the sign has a different period. It's 3x, so it's 2 pi over 3, right? So if 3x would repeat every 2 pi, then x repeats every 2 pi over 3. So we go plus 2 pi over 3n, plus 2 pi over 3n, and who writes 0 plus 2 pi over 3? No one. So it's 2 pi over 3n and pi over 3 plus 2 pi over 3n. And oh my God, like how exciting. How exciting is that? I can just...
I feel the tears rolling in my eyes.
Exciting stuff. All right. I wish we could have ended with that, because this isn't as exciting as that, but alas, you know.
But alas. Can you say this?
All right. No. This is the identity. So if you go back to the first page of 5.5, this is one of the cosine identities, okay? The second one, in fact. So second one on the right column. Now, suppose you're like majorly skeptical and you don't believe that identity and you want to prove that the Greeks got it right, okay? So let's see, did they get it right? Well, we can prove this one, okay? Because, what's cosine 2 theta, really? It's really cosine of theta plus theta, right? And if I have cosine alpha plus beta, that's cosine, cosine, sine, sine, right? So now I have cosine theta minus sine theta, sine theta. What's cosine theta times cosine theta? Of course. Cosine squared theta minus sine squared theta is what I have here. What's sine squared theta? Sine squared theta is 1 minus cosine squared theta. So now watch cosine squared theta minus 1 plus cosine squared theta. Cosine squared theta plus cosine squared theta. 2 cosine squared theta minus 1 equals 2 cosine squared theta minus 1. And there's the proof of that identity. All right?
Wow.
That is just so amazing. So with that, all of this homework will be due Friday. Tomorrow. Well, tomorrow's Friday. Tomorrow. Tomorrow's the 15th. The test is on Tuesday.